worked with deuterium-tritium mixtures too and obtained no positive results. That's why we decided to clear that problem and to demonstrate positive results to the wide community of colleagues. First attempt was made at the Minsk 94 conference, but we failed to do it in a good time because this experiment took the rearrangement of our detector and have done it invalid. Yes, have done it invalid. We remove the gamma shielding and we can't to discriminate gamma background signals. It is due to our poor facilities. Yes. Then we tried to do it at Moscow People's Friendship University at June 1994 and succeed to observe two successive experiments from two. Yeah, it is encouraged us, and we decided to go to the citadel of orthodoxy. Yes, we traveled to the United States and held experiments for 2 weeks at Professor Stephen Jones' tunnel laboratory. Yes, he provided us with all facilities. He has an excellent neutron detector, of course, but other facilities were poor because this tunnel laboratory is far from the base. Yes, from the base, and our vacuum system was invalid, and it forced our failure. Analyzing these negative results, I mean they are known. Our failure is known. We observed that not nuclear emission, no heat effects observed in this series of experiments. As for us, it means that no interaction of deuterium with crystal it was no interaction of deuterium with crystal. And our supposition is it is due to covering of the surface of the crystal with carbon film from a vacuum system. In further experiment we tried to avoid this difficulty, and we succeeded. That is the arrangement of mobile cell for demonstration of the effects elsewhere and so on. It consists of the quartz tube, yes, where the tungsten bronze crystal is situated. Then the tungsten cathode it's situated with a narrow gap about 1 or 2 millimeters above the crystal, which is used as an anode. Then a furnace to heat this crystal, thermocouple, and vacuum system, and deuterium flask. First, we heat this crystal up to 700 degrees centigrade. Yeah, then evacuate it and with under high vacuum. Yes, then apply high voltage to remove some sodium and measure the integral current. Measure the integral current to know how many sodium we remove. After that, we cool it down to room temperature and saturate it with deuterium. After that, we cool it down to room temperature, situated it into a neutron detector, and saturated it with deuterium. And some neutron events and heat peaks were observed. But this story was too long. First, we failed to obtain positive results, and analyzing these difficulties, we concluded that there is some more detail of equivalence scheme. Yes, it is a thermal electron emission from the cathode, which is due to heating of the cathode in this arrangement. It was not so in installation in Yekaterinburg. Yes, but it is obtained in the mobile cell. When we avoid this difficulty by cooling the cathode, all our results appear. Dubna Joint Institute of Nuclear Research provided us with opportunity of making experiment for long time in their facilities. First, they provided us with rather simple detection system, which consists of high voltage supply and block of counters. It is 40 boron fluoride 3-field counters with polyethylene moderator. Yes, then amplitude discriminator counting device and simple computer and simple software for documenting results. We add the oscilloscope to observe the form of the shape of the signal. Yes. After some experiments, we obtain reproducibility, and it forced the Dubna Joint Institute of Nuclear Research direction to provide us with cable connection with central processing center of Dubna, and we can now do all the analysis. We have two-dimensional time amplitude analyzer, but if we want, we can have 12-dimensional amplitude analyzer. I don't know what to do with 12 dimensions, but we can. Yes, but we can. Then some results. Yeah. It is a calibration of counter. All these 40 counters were parallel, were connected in parallel. It is a calibration by weak plutonium beryllium Newton source. The discrimination gate was from 5 to 9 volts, and the best sensitivity of this arrangement with this gate was some more than 2 kilovolts. Yes, and then some results. I'm sorry, my illustration material is poor. It is due to I have no hope to come here, and my results were on diskette, but I stand in front of problem of compatibility. So it is done by hand, and maybe it is just some curve. Yes, it is a typical pattern of background measurement. We measure background through all days and night, with 5 or 8 hour periods, and integration time was 10 seconds. And we obtain an average background level of about 0.2 per second. Yes, and some events were up to 0.7 per second. It is a normal distribution of our background. Yes, but working in Dubna has its features. I'll tell about it some later. Yes, and when this feature was in operation, I mean the experimental reactor IBR2, yes, when it come to its highest power level, our background became half a time more. It means about 0.3 per second. But the shape of distribution was the same. Yes. Then some patterns, typical patterns of our experimental runs. working runs. Yes, it is normal background when we treat the crystals, then large peaks of Newton emission. Newton emission, it is it may be commented. Yes, just after a few minutes after the deuterium input or after evacuation, we carried out such runs 15 minutes between deuterium input and evacuation, and obtained some repeatable events for two or three cycles, and then they diminished to zero. Then we retreated the crystal and repeated it once more and observed neutron emission again. It was encouraging results. Yes, after such a long period of troubles. Yes, and we became holes for metals. Yeah. But it was too early, because we obtained to observe a strange background. Sometimes where cell and crystal were outside the detector, we obtained large peaks of emission, by counter. I recall that this simplified system we use at first having the signal shape discrimination. Yes, only amplitude discrimination. And when we became to observe these strange backgrounds with high bursts of some signals, we became to provoke some disturbance. Initiation arc discharge in close vicinity of the detection system, but obtained no influence of such strong electromagnetic disturbance to detector. Yes, then we pay much attention of the shape of signals, and observed following results. This is a typical shape of Newton signal. Yes, and we observed such a signal in our bursts. My time is over? Yes? Okay. But simultaneously with this, we observed some other form of signal. Yes, and moreover, these events preceded the occurrence of Newton events for some milliseconds. Then maybe it is possible to suppose, not conclude, that the old idea of reactor fusion is alive, because such yes, and amplitude of this disturbance rose, and some of periods fit the discrimination gate. Yes, we suppose that it is some high voltage electromagnetic discharge in a crystal, namely in a crystal. Yes, because when we put the crystal with the cell to the detector once more, after treating this effects rose, and the quantity of this signal approximately relate as 50-50, and so on. Yes, my time is over. I thank you for attention, and one more acknowledgement. I want to acknowledge the organizing committee for inviting me and for funding of most of my expenses. Thank you.
Did you look for tritium And if you did, what was the branching ratio, neutron to tritium?
No, Dr. Svenasna, we didn't, we haven't done it, but we will done it using the facilities of Russian Physical Chemistry Institute. Dr. Lipson proposed us just now to do it, and we agree. We'll do it. We'll do it. But it is some difficulty, because only thin layer of crystal works, and tritium may be easily removed. Well, maybe easily removed because we evacuate the system after deuterium input. It is necessary to rearrange the experimental procedure, and then we will be able to measure tritium. Thank you.
Just one short comment, please.
Is it possible with those curves that you showed of the neutron signal and the applied voltage that we're seeing, the neutrons go down as the loading goes up due to the voltage? It seemed that there was maybe a connection there.
If I understand you right, you want to know if this signal connected with high voltage supply?
No, high loading, higher loading.
No.
Electrolytic situation.
Yes.
We find the neutrons go down as the loading goes up.
Yes. As for loading, of course, we obtain high loading by deuterium in very thin layer, about 100 up to 1,000 angstroms, but not in all the crystal.
No, that would be where the loading would be, say, in that layer. And that would be the
we can suppose the thickness of the layer by measuring the integral current of removing of sodium. Yes, but till now we didn't the analysis of surface to deuterium loading.
Probably you can continue your discussion.
Okay, thank you very much.
Dr. Svetkov is so that we will have next presentation, second presentation of Dr. Lipson.
Lipson. Can I help you? Okay, and it's safer if you hold, even if you hold. Okay.
Ladies and gentlemen, I'd like to report about new phenomena that connected with cold fusion or maybe cold fission. It is the increasing of absolute value of neutron flux at high neutron backgrounds in DKDP crystals upon the ferroelectric transition. Earlier in our works, it has been detected that on the phase transformation of the ferroelectric paraelectric type occurring on the transition of deuterophosphate of potassium single crystals through the carry point, the generation of neutrons is observed at an intensity exceeding by 2-3 times the natural background of the setup. In these experiments, however, the reproducibility of the results, even with controllable without defects crystals, did not exceed 90%. In most other works involving the observation of the nuclear DD fusion reaction in non-equilibrium deuterated solids, the reproducibility of the results was much worse. In this connection, the question on the reality of DD fusion reactions in crystal lattice and particularly on the emission of neutrons remains so far open. In fact, the neutron effects in deuterated solids in distinction from the effect of the generation of neutrons in usual DD reactions, in hot plasma, on accelerators, during fission of heavy nucleus, exhibit a number of peculiar features that do not permit to a full extent consider them as a manifestation of usual emission of neutrons. These peculiarities next. The first, emission of neutrons is unsteady. It has the form of fluctuation involving increases in the neutron activity of sample for short period of time. 2. In most long-time experiments, the signal to background ratio did not exceed 2 or 3 times. Third, there is no distinctly pronounced dependence of the intensity of the emission of neutrons on the mass of sample. And finally, the absolute intensity of effect, the count of neutrons with the subtraction of the background, depends on the background level and the efficiency of the neutron detector. The lower background level leads to the lower absolute intensity of the effect, and higher detector efficiency leads to the effect to the lower effect value. It is the most important feature. In this connection, a question arises as to whether the emission of neutron in a fluorescein experiment is a property inherent to deuterated solids that are in essentially non-equilibrium state, or whether the secondary neutrons are registered, generated by seed neutrons of the cosmic background interacting with deuterium in the crystalline lattice. In such a case, the non-reproducibility of the results on the emission of neutrons, in addition to purely material science aspect, will be connected with the non-reproducibility of the cosmic background, that is, with the probability of appearance of a cosmic neutron in the same space region in which the sample is found during the experiment. For purpose of verifying that hypothesis, we have carried out experiments on the irradiation by an external source of the neutrons of deuterated DKDP samples, being emitted 1 neutrons. Throughout temperature range of phase transition. The typical diagram of the neutron emission upon the phase transition is the next. On the higher diagram, it is the electric activity of a sample measured by thermostimulated depolarization technique, and lower diagram is neutron emission and neutron background. The effect for DKDP samples within temperature range of phase transition for 20 passes through Curie point was found to amount the next value, and with taking to account the detector efficiency, it was in 4p geometry 0.56 neutron per seconds. The count rate of neutrons in the range of lower than Curie point and upper than Curie point of the sample would also correspond to background level. In the experiments, we use the Californium source of neutrons. This is the diagram of experimental setup. This is boron fluor 3 detector with moderator this is the cryocell with DKDP crystals that temperature cycling through Curie point, and then the Californium SEOS. The efficiency in the system, crystal detector system and SEOS crystal system depends on the distance from the detector. In some cases, SEOS was shielded by means of standard polyethylene neutral stop C0 blocks in order to diminish the background. In connection with the rather rapid degradation of DKDP crystals, we use only 20 first transitions through Curie point. The experiments have shown that on the transmission of neutron flux from Californium SEOS through cryocell with DKDP crystal, in the process of ferroelectric phase transition, there is observed a real enhancement of neutron flux, depending on the efficiency of crystal detector system. This is dependence of absolute value of neutron emission on the background level. It was it can be shown that at the ratio detector background, cosmic background, about 100, it is plateau, and the amplification of neutron flux without SEOS and with SEOS is the ratio of about 20. It is this measurements was at constant distance SEOS crystal. In the other diagram, the distance from crystal was changed, and then this dependence is absolute intensity of neutrons subtracting the background on number of neutrons passed through DKDP crystal upon the phase transition. Dependence of excess neutron on the SEOS crystal distance indicates on the correlation between external flux of neutron across the crystal and the intensity of excess emission of neutrons from the crystal. Moreover, the form of function delta I indicates on the non-isotropic distribution of neutron flux. This is distribution of excess neutrons emission from the efficiency of detector. The curve 1 is the dependence of neutron emission for Californium SEOS. If we take to account the 4P geometry, we see for excess neutrons this curve. And without 4p geometry, it is curve 2. The obtained dependence of excess neutron emission can be naturally explained only in the case where we suppose that main flux of neutron from the crystal is directed according to a taper perpendicular to the detector surface, but not distributed in spherical symmetry 4p angle. The dependence of the count rates of neutron ions for DKDP crystal exposed to the external neutron flux during the phase transition through Curie point confirm a hypothesis on the generation of neutrons in deuterated solids as secondary neutrons initiated by the cosmic neutron background. In the fact, the absolute value of effect proves to be strongly connected with the background level of detector. The magnitude of effect increases with background level. At present, the mechanism of generation of secondary neutrons is still far from being elucidated. In our opinion, however, one of the possible models may be related to an injection into the DKDP crystal in state of phase transition of thermalized neutrons that will stay varying for considerable lengths of time, delta tau. During the time delta tau, a thermal neutron diffusion into the crystal can obtain many times a portion of excess kinetic energy from multi-phonon excitation induced in crystals upon phase transition. The bursts of secondary neutrons can be upon the next reaction when neutron is split up the deuteron. The bursts of secondary neutrons will case after the thermal neutron will have left the crystal. Let us note that short time burst of the emission of the neutrons of short duration will be observed in the process described, the duration being comparable to the time delta tau. The non-isotropy of distribution of neutrons emitted on the ferroelectric transition is in our view associated with the crosswise polarization of the crystal touched oriented DKDP crystal in direction 001. That leads to an azimuthal asymmetry of differential cross-section of deuterons in the reaction of generation of secondary neutrons. To understand the mechanism of secondary emission of neutrons requires making further investigation, including the application of the time distribution of neutron pulses and the monochromatic sources of neutrons with different energy values. Thank you for your attention.
Thank you. Any questions or comments? Yes.
I would like to draw your attention to the talk I gave in the morning and suggest that you could detect the presence of such bursts by simply taking account with and without a dead time circuit. It's a very simple method. I don't know whether I can.
With and without what?
A dead time circuit. The output of the BF3 counter, you send it through a dead time filter and count A without the dead time,
Говорит, что
count B
ты
with
можешь,
the
так
dead
сказать,
time, you
введением
will see the burst.
фильтра мертвого времени, значит, определить, так сказать, да, есть или нет. Согласен?
Окей, окей,
Simple, yeah.
окей.
Yes, please.
How did you confirm the effect of thermal neutron on the high energy neutron emission in your sample?
Some of new.
What neutrons? Effect of what?
Thermal neutron.
Thermal.
А, да, как ты разделяешь, да.
In some cases, we used the geometry of setup, then we shielded our cells with polyethylene plates and with 5 centimeter thickness, and then we thermalized our neutrons partially.
Yes.
Perhaps Bruno Stella made a similar experiment on the superconductor, and they confirmed the effect of thermalization of neutron from the source. And their result is if the neutron is thermalized, the effect becomes very big. Did you confirm similar effect of thermalization?
Он говорит, что, значит, какая-то группа, они, значит, определяли действие, значит, термализации нейтронов на эффект, оказали, что когда нейтроны термализованы больше, то эффект выше. Ты подтверждаешь это?
Okay, it is that when we thermalized our neutrons from source, we have the effect higher than from source of broad.
unfortunately, we had a beautiful, colorful drawings made by the computer by Gossi, but it's not drawn. So you have to look at this drawing that I tried to do with by a fax assembly. So the cell is within now is within, here is the blue, one is the thermostat toroidal net. The cell now is inside a dual flex, the black drawings you see here is a dual flex, is a glass dual flex. And this dual flex integrated with a capability to circulate water in a steam chamber in a way which makes the water to flow along these tubes and to come back all through the walls of the instrument. And you have water in through here and out from here. There are two solid-state devices in order to measure the temperature in and out of the water itself. The usual heater in order to make calculations. A level sensor, an optoelectronic device in order to look to maintain the level, the liquid level of the electrolyte at this constant level. A bubbler, and I couldn't draw all that detail. However, we have a nitrogen carrier which comes down, bubbles, and draws away all the evolved gases. And you see here this blue drawing is a apparatus, just a simple chamber, a vacuum chamber that has been added to the flask itself in order to prevent contamination by continuously flowing this chamber with nitrogen taken from the liquid nitrogen in order to have a helium-free environment where the leaks could occur in the most probably could occur in the cell itself. And what else? I think that this is what would approximately the main features. The same device was used also in other parts of the apparatus in order to try to have a helium-free environment. As for the performance of the calorimeter, you see here some example. There is a superposition here of the difference in temperature coming in and out. So if you take into account for the usual energy balance, you will have a ratio between power in and the difference in temperature, which depends from the flow in a linear way carried out from the gas and the other usual. It's an amount of heat that in case it goes in the wrong direction in order to give you the power excess. So if you have a linear relation, and this data shows that the relation is indeed good. It shows indeed a good linearity with the correct number, which of course this should be only the well, I didn't put here the units, but this is the info of 184 conversion. There's a way I'm not talking about, and couldn't maybe, and you have a good time constant of the apparatus, which is the one we show here, and the minimum power is estimated to be below 100 millivolts at a flow of approximately 2 cubic centimeters per second. Actually, the flow is where we are controlled by a gear pump. So the calorimeter has been improved, and from the point of view of the sensitivity, and from the point of view also of the cell itself, from the point of view, of the possibility of air contamination. I told you about the confinement technique. The confinement technique is based on the idea to have flow, current which flows through the cathode and taking freely pushes neutral ions to the blocking region where some material is put into or outside of the electrodes in order to have a blocking region of the deuterium ions. So the idea comes from this simple experiment that Gozzi made with gas phase, was a charging by gas phase, a palladium wire, this dimension with this pressure of hydrogen, and this palladium wire was used as it was in some way, so partially oxidized or has been deoxidized by reactions. So you see here, as a function of the distance with respect to the applied potential to the length of the wire, you see here we plotted the palladium versus the ratio between palladium and the actual loading ratio with respect to time. So you can see here that the oxidation on the surface of the wire reduces the rate of absorption and also reduces the escape size, number of escape sides in the side sections. So in time, a quite striking different behavior is seen between the deoxidized, where there is not such a blocking destruction of the surface, and the oxidation and the oxidizing material. So the palladium wires of different diameter are now used, and different extension of deuterium blocking regions, and different also arrangement, special arrangement. Also, the amount of current, confinement current that can be used has been now increased up to, if I remember well, 30 amperes. Maybe I'm not wrong exactly, but the order of magnitude is the same. So if one now looks at the voltage, which is called in our jargon the voltage of confinement, which means the drop of voltage which is due to this confinement current. When you have palladium wires of different dimensions and wells with the same electrolysis current running, but with different different current of confinement as a function of time, you see that mainly, particularly with the smaller diameter, it's not clear from this figure, but it happens also with the larger diameter. The derivative of this voltage with respect to time does increase with respect to the ionization, to the current of confinement. So here is tabulated data, scheduled tabulated data where I used that the derivative of the voltage does increase with this confinement, the amount of the confinement current at the same level of the electrolysis current density. So the Gozzi published a paper on that, and they made some prediction about this behavior of this derivative, and the experimental point seems to fit, at least for the first part. After that, the prediction goes in a quite complicated way, is quite well respected. This basically is the structure of the experiment, so a multi-cell experiment with this confinement, with the study and the exploiting of these confinement properties in order to have a good dose integration in some certain region of the cathode itself. So what remains now is to speak about the pattern, which is the helium measurements we are performing actually. And the main goals we had in improving our apparatus were to improve the offline measurement. We made in the last experiment, a measurement with a relatively good, also a full magnetic instrument. And so we had to work in an offline situation. We had to collect gases and go to our spectrometer and make their measurement. So improve the offline measurement and also to add an online measurement in order to avoid any possible pollution during the manipulation. To have possibly a better time structure, I mean a repetition rate of the measurement which could or continuously or with a better repetition rate which would follow the variation in time of the possible phenomena with a better resolution in time. And frankly speaking, also to release some of the pressure I personally have, because I will make a new man from the other colleagues in order to have the instrument free from another experiment. I always have. People always ask me, when did you begin, when did you finish? And you know, it's quite a long way to do this experiment. So one of independence is quite important. It seems not very scientific, but it's very important. But we also try to have this online measurement having a similar sensitivity, of course, trading off with the resolution in some way, but because we can take advantage of the excellent it's a very low amount of deuterium which comes out from the lines that is before also my working with Daniele also really already seen it with the collection of the line, with the collection line. So I have to briefly let you remind for those who were there now approximately how it works, our offline measurements. There is a mass spectrum, a mass spectrometer. This is a collection flask which is connected to a line, the inlet line. The only two important things to note here are that this flask is full of nitrogen with some amount of deuterium and it's helium or so. So after admitting to this connecting line, the nitrogen is absorbed in this active charcoal maintaining the nitrogen temperature. So the pressure, total pressure goes down, and after that it can be emitted into the mass spectrometer. And during the emission, we close off the pumping in the ion source, so that pumping comes only to the narrow slit of the mass spectrometer through the other pump, which is into the mass spectrometer. As a consequence, the helium signal has a kinetic inside the ion source. So this is signal on the right time. So rises at the opening of the valve and decays quite rapidly, but decays. We could also check the separation of deuterium and many other features and add some amount of air in order to in situ calibrate the instrument. So the only improvement that has been done is to this type of measurement is only from the experimental point of view, only the improvement of the line itself, of the materials that we have KF joints, now we have a VCR joints, all metal joints, but this is not really very important. However, during the last experiment I told you we had also a correlation with the neon. We began to measure in the course of the experiment. It was not so easy. However, our resolution was good to measure helium. You see here how crowded is the spectrum, possible spectrum of neon 20 plus in the region where one has to look at. We into being able to look at this neon. I thought that I had some more time. I thought that I had some more time because I was connected to. Oh, that's the reason why. That's the reason why. I'm sorry. But it's not a long story, I hope. So we had a little bit problems, but I think we succeeded in measuring neon with a fairly good resolution. I just recalling you the question. Now, approximately since the beginning of this neon measurement, we had a different idea, but we didn't pursue it at that time because we were running through some other reason. And actually, we proposed to look not at the neon plus, but at neon plus plus. I mean the double ionized neon. This is a literature data, very old, but good literature data about the ionization efficiency, the curve, what is called the curve, call it the ionization efficiency curve of neon plus plus. So you see that you have to work at quite high electron volt energy. It means more than 70. You have to have at least 10, 100. And from what you see here, you should lose a lot of sensitivity because you should have at this level the order of 1 or 2% of neon plus plus with respect to neon plus. But in the usual instrument, commercial instrument, normally there is a magnet in order to increase the sensitivity, which usually causes an increase of the double ionization. So it's in the order of a few percent. So you are losing sensitivity, but you are working at mass 10, which is a region of mass where, in my opinion, you should not have any superposition. So, in the meantime, we have a quadruple mass spectrometer. These are the main features, and the features you have to note here is only that the mass range, when operated in a high relativity, high resolution mode, is only 1 to 24. And so one could possibly also work at 20, but I will show you there is a superposition. We selected a gas type source, which means that we have a source which has a low conductance with respect to the main chamber, the vacuum of the main chamber. So in a way we are simulating what we do with the magnetic instrument. We are admitting our gas to an ion source which is not pumped freely. And this increases the sensitivity. The setting, of course, you have to have quite a lot of ionization energy. We actually work at 100, we could work at a little bit higher level. So this is a plot of the logarithmic plot of the ion intensity of neon 20 with respect to the neon 20 plus plus. So we have the number 10 mass and the number 20. And you can clearly see from here, remember it was a logarithmic plot, that there is a superposition of at mass 20 because the kinetics you see is different from that of the mass 10, where you only have the neon. So also if we could possibly work at mass 20, we do not have enough resolution to resolve at mass 20, so we work at mass 10. This is a layout of the experiment as far as all the lines, connecting lines are concerned. What is to note here that we have the carrier gas which goes through the cell to the recombiner and through a palladium sponge trap. So it comes out relatively free of deuterium. From here to there is exactly the same type of arrangement, completely different from the material point of view, but exactly the same type of arrangement that we have in the offline measurement of the magnetic sector. In this case, we have 150 cubic centimeter flash, all metal flash, which is effectively 500 cubic centimeters, a trap, a charcoal trap, and only after having absorbed nitrogen, the gas is admitted to the quadruple mass spectrometer. A feature which has been added, I might already show you, as far as the cell is concerned, is a cap which is protecting from the possible contamination, and also the recombinant is enclosed into a nasal volume which is continuously fluxed with nitrogen taken from the liquid nitrogen. We also have an arrangement in order to be sure that also the exhaust line will go to a helium-free section where, by the way, one has to suck the gas in order to refill this vessel when it has been emptied to the mass spectrometer. And in order to prevent that this sucking will put the line under slight vacuum, we have something like I would say ballast, a large reservoir of nitrogen helium gas. The other feature is a complete automatization of all these procedures. These are all electrovalves, and so you can arrange the timing and so on in order to make a repetition of the measurement in time, also during the night. This is the time behavior of the helium and deuterium signal. Of course, they are scanned with respect to time, and in this case, kite cycles. And so it's a similar behavior we have seen before. If the helium rises at the opening and goes down. Actually, the dosing valve is always open. What is open is only an electro valve, which is an on-off valve. So the valve is always open. In time, the signal goes down in something like 10 to 12 minutes, or something like that. You see also in this case, the deuterium signal remains up because of the continuous because the trap itself, or the charcoal trap itself, acts as a continuous reservoir, which gives you the same pressure of the deuterium outside of the mass spectrometer. This only to give you an order of magnitude. The resolution one can achieve actually is better. We have this resolution now. We are working with this resolution. The resolution we can have is actually slightly better than this. And if we compare it with the magnetic resolution, of course, we are quite a lot at a lower resolution. You see here is our magnetic resolution approximately, and this is the quadruple resolution. It's not the best possible, but it's the one I think is enough in order to be sure that one is looking at helium itself. Is the same, but at much lower amounts of helium and deuterium emitted to the ion source. So, what's the sensitivity we have with this apparatus? We have here some data. So there's a decompare with respect to 10 to the 12 atoms, tera-atoms. And the main feature to look at this is that we have really a large scattering, at least much larger than I expected to have. And possibly also a slight dependence with the amount of helium introducer, which is in a way to say that it's not completely linear. It's a slight dependence, but you know, it's what maybe it is. I don't know. We have to accumulate more data in order to see that. Actually, we are now working in a larger sensitivity region, actually approximately 2 times that, by setting differently the ion source potential. And so, by translating it to size, we have approximately the same sensitivity we have with the magnetic mass spectrometer, approximately the same. So, we are looking into a region which is depicted here. It's a different way to present the same data. You have the decompare which you can measure with respect to the helium ppb level into the vacuum gas. And I have drawn here a range of detection which actually are not the range of detection limits of the mass spectrometer. These are the range of detection limits of the overall assembly itself. And it depends from a number of, there is also an instrumental, a purely instrumental sensitivity, of course, but it depends also on the amount of deuterium you have, because we do not have, with that resolution, the capability to measure when there is a lot of deuterium. We usually do not have deuterium, as I told you, but if it happens, we will not be able to measure after some level. And also, it has to, well, the minimum sensitivity I try to draw here depends also on the amount of neon we can safely say we can measure. And this is still, at least for me, a little bit a problem. I'm not sure exactly now what is the minimum amount of neon I'm sure to be able to measure. And so what's the ratio of helium to neon that we can safely consider to be a clear indication of no contamination of helium. The type of measurement one has to do is here, depicted on logarithmic and on the linear scale. one has to look at the helium, one has to look at the deuterium. The instrument is a multi-channel instrument, so you can follow different masses in time. You can look at the helium, the deuterium, at the valley between helium and deuterium, so the mass in between, and at the neon itself. This is a relatively extreme case. Not maybe you see 2 dB is the signal, of which the order of magnitude of the signal, and which gives also an indication that the resolution is enough to be quite sure that helium is there and not something else. Finally, there is about I told you we are looking to have a better repetition rate. We are not looking continuously at the gas. We are collecting the gas and we are emitting it. So we have to look at the time structure in a time scale. And so we are trying to characterize the transport properties of our lines. So by injecting a specific amount of air in the line approximately before actually it's been done before the cell, we look at the signal of helium and neon with respect to time. And to my surprise, to my personal surprise, at least up to now, we observed that helium and neon almost since they travel together, and since they in some way travel together, they have this shape. And I expected to find the helium diffusing in a much larger way. Approximately this maximum corresponds drop on the orders of order of magnitude on the time to travel by calculating the flow of the nitrogen carrier gas. But the amount of helium which is recovered here is, well, not an order of magnitude, but something less than an order of magnitude less than the amount would have been recovered if injected directly into the directly into the conventional collecting vessel, so that this also lowers in some way the sensitivity. And so we are trying to have a better structure by reducing the volume of some of the volumes that are on the lines that are really not needed so large. I would like to finish my talk giving what are, in my opinion, 2 warnings. One is that it remains to be seen that if we will be able to look at the neon with the sensitivity and the helium to neon ratio with the sensitivity, like already told you about that, enough to be able to check with sure that there is no sure contamination. We do almost what we could in order to avoid. And up to now we have something like 3 weeks of length approximately, and there is no helium detectable above approximately, but the worst of the lines has approximately less than 1.5 parts per billion now. So I'm confident that there is no leakage, but I don't know if we will be able to look at the neon iteration. So one of the warning is that in some cases of very large amount actually of material, really very large, it's completely separated the signal. And with some setting of the answers, we had what I personally think now is an artifact, exactly at the same mass of helium. So with large amount of deuterium, maybe that some precursors that are described in literature for the particle mass spectrometer is operated in our condition at that particular moment in that particular setting. I'm not implying that anybody else can add all of this. No, it's not a universal. Finally, let me see you. I have the transcripts of my talk and all the other people. Of course, Manili, myself, these other people. It's a cooperative approach from the chemistry department and the group of physicists from the Istituto Superiore di Sanità in Rome, and all these people that come from the University of Rome, the chemistry department. All these people come from the Istituto Superiore di Sanità, Laboratorio di Fisica, the DNF, and also section of the DNF. So if I'm lucky enough, you are not spite of the lunch, of the hours, and of my work, you are not completely asleep. So thank you. People are still alive.
Two papers are present here, 322 and 325. Yes.
That's a very nice and serious talk. And clearly a very important improvement in deuterium against helium-4. But always, sorry, but it's also important to worry about the helium-4 contamination. So the question is there an easy way to confirm what you're doing? The way to check your experiment would be to use a 50-50 mixture of hydrogen and deuterium and look for helium-3. Because helium-3 does not have the terrible problem of contamination. And this should give you a much higher cross-section and be a very good way to check things. And then as a second check, you can vary the ratio of hydrogen to deuterium.
That assumes that hydrogen will work in a palladium lattice, and my theory proves it can't.
Sorry, I didn't get it.
That's the usual way, you know.
Just let me
to disregard.
let me answer. Now, sorry if I remember. Now I understand your question at the Maui conference. I didn't understand, frankly, at that moment. I understand what you mean, but you have to understand also that it's not so easy to follow many different masses in the magnetic instrument we have. It's an old one. We have to choose something. So to measure helium-4 and neon-20, we had enough time. I mean, the signal duration was enough time to measure these two. To look at helium-3 is more difficult as far as the resolution power is concerned. I think that the magnetic instrument can resolve, but actually I don't remember exactly the figure, so I don't know how much can it resolve, so it's not so easy. And coming now to the quadrupole, it's impossible to resolve helium-3 from H3. So one has to, in a way, do an experiment only to look at that as for the magnetic instrument is concerned, our magnetic instrument is concerned. So I get your point, but from the technical point of view, from the measurement itself, there are some difficulties.
Isn't it possible to get another spectrometer?
No, frankly, to be honest, we have a lot of pressure not to use that magnetic instrument, not for the particular field. I mean also because the other people want to work with this magnetic instrument. So it's not so easy for us to settle the apparatus for this measurement. So if we are using the quadrupole, it may be possible to use the magnetic for the other instrument. But frankly, I do not know if the experiment we are now running or beginning actually to run, we will be able to use the magnetic instrument because we are late on the schedule and we have to wait for it. This is what is openly, I told you openly, the situation. However, I will consider it from the point of view of the technical point of view of suggestion. I didn't understand it now. From the point of view of the putting a different environment, I can only say that Goldsey told me, forget it.
Last simple question.
No, well, I mean, it's not a question, it's a comment. Just to tell, I mean, my good friend, that Morrison is implying that you have no good judgment to look for helium-4 because there is a background and there are better ways to do things.
I don't think so. I think I explained it. What
no, but because you see, the point is, it's not going to be. The point is that he's implying that he's not going to be convinced by your measurement of helium-4 above background because there are always contamination. So you have to do something else in order to convince him. So this is a usual thing.
May I make a joke? Okay. I didn't know. Sorry, I didn't know Morrison before. Now I understand that as he only asked me this question at Maui, and now I think I did a pretty good job about this because this is my understanding of the situation.
Thank you for your answer.
Let's go to the next presentation.
tutte queste cose. Ma questo non conta, perché devi sempre qualcosa di più.
Le prove di democrazia per l'utenza.
You suppose it to work?
I think it will work. Yes. And also try to hold this. That will make it.
Okay, title of my presentation is Search for Helium-4 Production in Palladium Helium System, and it is our old staff of Torino ENFM with some newcomers from Fiat that we hope that they continue to work with us. So, summary of my talk is the following. Introduction, I will briefly describe the feature of our helium-4 spectrometer. I will describe with some details our cell. I will report on our first experimental results, and finally, which are our conclusions and perspectives. So, as the introduction, let me remind that just from the beginning of the cold fusion story, our group, I had the opportunity of hearing Martin Fleischmann at the first talk in Lausanne and CERN, and so our group was deeply engaged in searching for some unambiguous signal of cold fusion, and as many as our colleagues, we focus our attention on the neutron detection by using the gas loading technique, and we set up a spectrometer that is still used, but it's not our first priority, in which we use the double scattering technique, time of flight detection, and so on. And I think that we get quite nice results in the sense that we have an energy resolution for the 245 MeV neutrons of 1 MeV at full Wigner maximum, with an efficiency which was rather poor. It was something in the order of 10 to the minus 4, but without practically eliminating all the cosmic ray background and so on. Here you have the references for the spectrometer, and I simply remind to you which were the main results that we have published. We used a cell, titanium mostly, and after deuterium, with temperature cycles in order to go through the change of phases, the phases. And the results that we have, I remind briefly. On titanium, we observe twice, after long runs, signals corresponding to 2.5 sigma and 5 sigma, by the subtractions, we think, by comparing all the times and deuterium and hydrogen loaded samples and making all the proper subtraction techniques, being sure that all apart these effects were consistent to zero. With palladium, we consider as significant results exceeding 2 sigma. In palladium, we have a signal lower than 2 sigma, so okay, I report that it is published, but we have never considered that as so much significance. Now, some months ago, before the Maui conference, we were just, we had several group meetings, and we had to decide whether to continue, how to improve our search. So one logic thing was to try to improve the detection efficiency of our spectrometer and continue on our neutron effort. And in fact, we had also, by chance, we had not problem of money, because we had by chance, by some dismiss and high-energy experiment, possibility of improving by a factor of 10 the number of detectors. So, and But at the end, looking not at the money, but the big effort that was inside to put together, calibrate, and so on, 100 neutron detectors, knowing just from the beginning of Fleischmann and Pons that the neutrons were very few, we decided to keep our spectrometer like it was, and on the contrary, to devote our efforts on something new development, which apparently was of a search for nuclear ashes, that helium-4 was apparently more promising, and even if it was not our field, it's the typical field of Chile and others, we decided to embark us in this sort of adventure. And so let me describe briefly how I will show the results that we have, how we have still, on the time we have here our all neutron detectors, but we concentrate on that. Forget about the variables, bypass, and so on. The essential point of our system is a cell that I will describe, the spectrometer, which is a null-vac spectrometer, 2 filling bottles. We have a titanium getter pump, which about 50 grams of titanium, which is rather useful in order to lower considerably the deuterium content. We have also an external location for an external flask in order to use the spectrometer sometimes to examine the gas content of other experiments. For instance, last week we examined the Piantelli experiment content. And finally, we have here some calibration bottles for controlling the system. Well, I will not show to you the characteristic, or very briefly the characteristic of the spectrometer, the ULVA spectrometer, which can work in high resolution and low resolution. Here you can see a picture of our arrangement. Here is a neutron detector. Here is a small helium-4 spectrometer, and all this sort of this is an array of variables and so on doing the function that I had described before. So let me briefly show which is the resolution of our spectrometer, which is not very different from that Dr. Gili has shown. This was obtained, of course, with the calibration by having simply our calibration flask filled with nearly equal content of deuterium helium-4, and it is working right properly. And here I may show to you how the efficiency of our getter pump. This was injection of gas at a rather low pressure. It was in fact 3 × 10⁻³ millibar, and we arrived at the background level in about 600 seconds. This is quite important in order to understand how much time we need before going down with the deuterium content. Now let me describe briefly the cell. In the cell we try to, is always a gas-loaded cell, in which we try to improve the loading ratio by electromigration or Cohen effect, as you can call it as you wish. These are dimensions of our palladium sheet, 8 centimeters by 1 by 50 microns. And we use sometimes gold-plated ends, which means that the 1.5 centimeter on both ends were covered by a gold coating. You must be careful about that, because when I will report about the loading ratio, you have to take into account that you always refer to the full length of the sheet. Now, if you take into account the resistivity of our sample, and you look at which is the current that you have to pass through in order to get this voltage along the 2 electrodes corresponding to this field, you get this value. And of course, what is at first sight, it would be useful to work at the maximum or high electric fields. But, of course, you have the problem that you have the Joule heating, which raises the temperature. And this is an experimental plot in which we show which was the Joule heating of our system. The cell was in contact to a water circulating water circuit at 20 degrees. And here you see the effect of the Joule heating. And in fact, after a longer period of experimentation, we choose to work, you can see at a high current we reach rather more than 100 degrees Joule heating. So we choose to work at relatively low field values corresponding to typically this sort to a field of 0.25 volt per centimeter. So this is a picture of a cell. You can see the sheet, the palladium sheet is just inserted between these two copper electrodes, and here you have the temperature gauge at the center. We paid a considerable attention to the control of the loading ratio, which shows to be one of the most critical parameters. And we used both methods of the resistance method, and of the thermodynamic measurements. And we have quite a nice control. Here you have the measured ratio of the resistance as a function of the loading compared to the resistance at zero loading, and on the abscissa. And the coordinates, you have the resistance that you can calculate if you assume, by assuming the Mekubre fitting polynomial as a function of the loading ratio. So here is the measurement, here is the resistance as evaluated by this formula. And you see a rather close agreement. This is quite a linear agreement, so with an error of which combining the two is plus or minus 3%, we are, I would say, absolutely sure of our loading ratio. Now, in both measurements, you have to take into account that you are measuring the average loading ratio, because just by the application of the electric field, we may expect that there is a profile of concentration along the palladium sheet. And so, one of our younger students has developed a simple model in which he takes into account all the effects, and considering the parameters of the alpha and beta phases, not the gamma phase. And here you can show a correlation among the measured alpha, which is here, and the simulated alpha. Well, there is some difference, but due to the crudeness of the model, it can be still acceptable. What is quite interesting to see is how you can expect time evolution of the loading with the time. So here, with the black curve, you see the loading after approximately 3 days of loading without field. When you apply the field, after 120 minutes, you see some spike appearing just near the cathode and evolving more and more with the time. And again, how much time? How much time I have? Okay. And here again is the simulation that shows this is the mean value of alpha that, of course, is increasing because it's starting to charge at the center and after to diffuse at the sides. This is the maximum value of alpha, which is reached. And here you see how, after applying a voltage of typically something like 1.4 volts, how there is the increase of the average alpha and of the local alpha. Now, let me go to the results that we have up to now. We performed experiments on four different palladium sheets, and the dimensions were more or less the same. Difference is that for the last we don't use the golded ends. Also concerning the treatment, in this case we treat with nitric acid. These two runs were essentially in order to characterize the system, were not performed with the neutron detector and with the helium spectrometer. What we learned from the first run was that apparently we got better results at higher pressure, and here there is the pressure at which the run were performed. Here you have the maximum loading ratio that we observe. Again, you must be careful. This is the maximum average. So, which is the maximum local depends on the model. This is, I stress again, because sometimes is a matter of confusion. Is the average that we could measure. Of course, in order to give the maximum local, we have to rely into some model, and of course, before relying on some model, we must be rather cautious. Certainly, locally, we expect that you have reached a considerably higher value of alpha. This column shows the effect of the electric field in order to increase alpha. I will show some results after. And here you see that at low pressure, the fact of applying electric field was good in order to increase alpha. Here you observe in this run a rather steep, a rather regular increase of the loading ratio corresponding to this value. And again, here again we observe at two times good effect, let me say, in such a manner, of the electric field. Of course, here the experiment was not connected with the helium spectrometer, so certainly we could not measure the helium content. Here, yes, and in one case, perhaps we have observed, and we showed you the results, an excess of helium-4. Now, let me show the experiments, well, at least one of the significant measurements of the effectiveness of the electric field increasing alpha. This refers to these experiments, and you see here in blue you have the electric field. You see that we were increasing alpha simply by thermodynamic. When we applied the field, it was a decrease, but of course due to a fact that there was a rise in temperature of the palladium sheet, and after the electric field gives a slope which is larger than that and before. And what is more clear is the last. Here is not plotted, but in fact we did some rapid variations which is not plotted here, and as an effect apparently we had a rather sharp increase of the loading ratio. And this is the other experiment in which we observe a constant increase of loading with the field, which is again always here in blue, correspond 1.2 volts, and compared to the case in which there is no field, and which is the last, what is going to zero, and this is the last part of the curve. You can tell to me why you have. Okay.
You start concluding.
Yes. Okay. It was simply a blackout of the acquisition system, so it's clearly we could imagine that it was going like that, but certainly we cannot assure that. It was as usual during a weekend, this blackout of the acquisition system. So let me show briefly the results. Essentially, I have one result, or perhaps two. One is, you may see, this is the palladium sheets after how it was looking after, and you see there is a blackening just near the cathode when we expect to have an increase of the concentration of the alpha. These are the plots on the helium measurements. This is before, this is, let me say, the background, and here you have the signal, so you have an effect which is in the order of 25%, if you believe in it. And my conclusion are the following. The electric field seems to enhance alpha. Perhaps in one experiment we have observed helium-4, and if this 25% is correct, it will correspond to 1.4 10 to the 10 atoms. No 2.45 MeV neutrons were observed all along the experiments. And it means that if we believe in this number, we have, and we take the number, the limit, this is the lower limit on the neutrons emitted, we have this sort of ratio among helium-4 and neutrons. And concerning perspective, we have constructed a new cell in which temperature is not only measured at the center, but also at both ends in order to understand a little bit more what is going on. And we plan to, is also machined in order to work at increased pressure. And our plan is to do for this year measurements on different sheets and to do also blank measurements with hydrogen.
Could you show that you showed a photograph which showed increased blackening due to increased alpha? I didn't understand what that was.
This is how the cell after the run, and you see that this is the blackening which is just in correspondence of the cathodes, and if you compare that with the profile, is a sort of is not a demonstration, is a sort of indication that the model that I showed to you before, that after applying the electric field, you have this sort of profile of alpha.
Yeah, but what causes the blackening?
I don't know.
Any other comments? Well, thank you for next presentation is what you look at those or the viewer.
I've brought my partner, Roger Stringham, along here to help out, and Roger's going to introduce, since we use such a different method than most the electrochemists and other people here, Roger's going to just briefly run down a little bit about the cavitation and bubble physics that we make use of.
Thank you, and I want to thank Russ for letting me explain a little bit about cavitation, which is something rather unique, I think, in this area. The first thing I would like to show you is a view graph demonstrating the two different kinds of cavitation. One you find in the sonoluminescence process, which is stable cavitation, and the other is found in transient cavitation, which is the cavitation that we use in our process, which is this, this right here. What we have here is a plot of time of one cycle, which is, we use a frequency of 20 kilohertz, which means that the distance, the time for one cycle is about 50 microseconds. We look at that plotted against the radius of a bubble that is generated in heavy water. And what we find is in the low energy system, which is an acoustic energy of, we'll say, something less than 1 watt per square centimeter, what we find is that the bubble will increase in size up to a point where it will then radically, adiabatically collapse, giving off, if it is sonoluminescence, giving off a bit of light and oscillating quite rapidly, and then recovering, and then going through the process again. And this will happen at every acoustic cycle. However, in our system, we put in a little bit more acoustic energy, and what happens is that the bubble will grow, and again, collapse adiabatically, but a little bit faster and a little bit more radically, and it has no recovery. And what happens is it basically will destroy itself. Now, if the bubble is on a metal lattice, then some interesting things seem to occur. I'm not going. These are some equations, but they're really. You can get these from any reference or any recent paper, and they're very exciting and interesting. But depending on how far you want to carry this, you can get almost any energy density that you like. It's suspect to very rough interpretations. Now you see here is a very unique picture of a bubble and the jet that is formed. And the jet is what we call as a micro accelerator, where the bubble, as it collapses adiabatically, it basically turns itself inside out in a toroidal type of system and injects into the surface the very hot plasma-like dissociated species that are in the bubble. You know, what we have in the bubble basically is heavy water. Dissociated heavy water in the later stages is focused at a small area on the lattice and pumped into the lattice. And what is curious, if you have a number of these bubbles happening sequentially, you'll get a great deal of loading at a very small palladium. Next, I'd like to show a apparatus that we use. We have several. The requirements that we look for in this particular apparatus is it's completely made out of stainless steel. We have a circulation system of light water, and which is an energy transfer system, and we use the energy that passes through the light water, goes into a heavy water system, which is in the reactor, where there is a palladium. iso particular rate, so we get a cooling profile for each component. From the calorimetry, we can get an energy balance. Now, if we look at a heater would run, this is the ratio of output to input power versus time. If we were, the calibration would run along this point here. I don't have the points, but the calibration of the heater is 1, where the input matches the output. Now, when we use the cavitation and we look at the input and output, we find that we get a excess energy, and this excess energy over a 24-hour period can be quite substantial. When you have for this particular device, running at 1.2, a ratio of 1.2 is somewhere on the order of 16 to 70 excess watts generated. And with that, I'd like to hand this over to Russ and discuss some of the very exciting results that we've had using this device. Russ, you want the microphone?
Roger. Roger left. One of the interesting calorimetry graph plots that we've had here, which shows our heat after the system turns off, which is an effect that we also see. I think Martin reported it as heat after death. But we typically, this lower curve here is what we would expect to see based on the cooling curves of the system. But we see the shaded area is actually excess energy that we're measuring based on the calibration of the system, well, cooling curve calibration. And it's an interesting curve in that it shows these bursty events. It's a 6 or 10 watt excess that bursts, comes out over a number of minutes, after the system, after all the power of the system is turned off. So it continues to produce some excess heat. However, this is the nuclear measurement section here, and I know a lot of people have been interested in the nuclear results. We started several years ago looking for helium as a logical product in this, and the first results for helium we've seen using a mass spec at SRI, not in McCoubrey's group, but in a separate group there. And we thought, well, okay, that's a few good results there are very interesting, but we should repeat those at a second location. So we conducted more experiments and repeated those results and sent samples to the U.S. Bureau of Mines Helium Field Laboratory in Amarillo, and saw, again, helium-4 signatures in the range of 50 to 60 parts per million. So given that atmospheric helium is at 5.2 parts per million, we were at about 10 times atmospheric levels at that point, and that represents 10 to the 17th, thereabouts, atoms of helium or being seen in the system. However, last year at the conference in Hawaii, where we presented that evidence, Professor Huizinga said he wouldn't believe repeated experiments showing helium-4 measured at either SRI or the U.S. Bureau of Mines Helium Field Lab. He would only believe them if we did them at Rockwell International Rocketdyne Laboratory in Canoga Park, California. So we ran additional experiments at Los Alamos National Labs last April. Took the samples archived in stainless steel bottles and sent them with the help of EPRI to Rocketdyne's laboratory in Canoga Park to Dr. Brian Oliver. And Brian, and indeed Professor Huizinga's advice was tremendous advice, because in those results we saw 500 parts per million helium. So we have Professor Huizinga to thank for that. Furthermore, Brian Oliver does such superb work that we were able to also measure the helium-3 ratios in the samples. So the helium-3 sample, we looked at samples of experiments of both palladium and titanium, which we like to use in our system. And we found some interesting results. This first result here is a run we don't have 100% success. Sometimes some of our experiments just don't make heat, even though everything has been operated the way we thought it should be. Some of them fail. So the first one is a failed. The first one we thought we might get something, but we're not sure. But we didn't see any significant increases in helium. So that's sort of a good background, and that says that the helium concentration in the argon gas might have been 0.4 ppm, no greater than that. That actually turned out to be the detection limit at Rockwell. Actually, no, that was the amount we saw there, so we assumed that was the background in the argon that we were using, which is high purity argon. However, in the next experiment, which is with a titanium run, we saw significant increase in the helium-4 in the system, as well as a very significant increase of the helium-3. Now, it's a little hard to read this, but what you expect in the system is that helium-3 to helium-4 ratio should be 1 part in 800,000. That's the terrestrial levels anyway, the ratios. This turns out to be 1 part in 180 helium-3 to helium-2, helium-4 ratio. So we're about 1,000 times the normal ratio. Douglas Morrison earlier said that we should really consider helium-3, helium-4, the way the astrophysicists do it, say it's 1 part in 10 million. Well, that would give us 2 more additional orders of magnitude security that we've produced at unusual isotopic ratios. In the palladium system, we did not see helium-3. The helium-3, in fact, turns out to be below the level of detection that we had at Rockwell, which suggests that it's less than 1 part in a million. And so we appear to be sending helium-3, but it's close to 1 part in a million. So it may be that we're sending helium-3 both directions, both increasing the helium-3, helium-4 ratio in the titanium system and producing a more only helium-4 in the palladium system. So we think we're working pretty good on that. We also, furthermore, we looked at the metal samples. Brian Oliver has been working for many years at Rockwell, analyzing different kinds of metals that are subjected to neutron bombardment, and the neutrons produce helium in the metal, and that's an indication of the neutron damage to the metal. So we looked at helium in the metal targets as well, in both titanium and palladium. And these figures represent a range that we saw quite a number of samples, some of which were obviously going to be blank samples, did not produce reactions. But so the range of helium-4 that we saw ranged from 0.2 atoms in a small sample, roughly 10 milligrams, to 8.3 times 10 to the 9th. And generally, that represents, the high numbers represent about an order of magnitude increase of helium in the lattice than one might expect were it the virgin material. It's not a substantial amount. In the titanium, we see that go up by about another order of magnitude, so somewhat more helium is retained. 2 orders of magnitude helium increase is found in the lattice in titanium. So we think that's some pretty interesting nuclear evidence. The total helium that we're measuring is about 10 to the 18th atoms for an experiment when we base on extrapolating the sample size back to the experiment, because we're unable to take a complete sample of all the reactor gases that are produced. So we find that's pretty exciting evidence. You know, one of the things that got us interested in this is that we look at the metals that are in our reactor, and they are melted and destroyed by the reaction on frequent occasion. If you zero in on this sort of thing with an electron microscope, you see that near the edges of the hole, it's a rather pitted, crater-looking surface. As you progressively zero in on it, you find that the surface is very roughened, and these wonderful little features start to appear. There's additional ones here. They have these little round